is continue with this theme of searching for simplified descriptions. In particular, in this context, we're trying to build a model of the probability distribution for many variables. And whereas yesterday the primary example was a flock of birds, today we're going to talk about a network of neurons, but we have a few things to do before we can get there. So I would like to do a little bit of, let's say, traditional physics teaching to set the stage. And this is a set of ideas that are very deep, and I guess Stefano was saying, you know, you could give weeks of lectures about the subject, so I'm going to talk for, you know, again, the sort of canonical half an hour of background, and then we'll try and do something that's more relevant. So this is simplification by coarse graining. And I'll tell you exactly what I mean by that in just a moment. For the physicists in the audience who know these things, just so you know where I'm going, basically we're going to talk about the renormalization group. And why it has this complicated name is a bit of history that is not terribly relevant. But let me give you the general idea. And this really goes back to one of the things I said at the beginning, that, you know, if you want to describe what all the molecules are doing in this bottle of water, that's very complicated. And if I dissolve different things in it, then I get a slightly different set of microscopic interactions. But somehow macroscopically, the flows obey the equations of fluid mechanics, and that doesn't depend on the details of the molecular interactions. So we understand how that happens. That is to say, how do you go from all the detailed microscopic interactions to a description of macroscopic behavior? And how it is that in that process, our description becomes simpler and more universal? Okay? And so what I'm going to do is I'm going to basically dive into a very simple example. And I hope you'll see at least the outlines of how this works. Again, this is a big subject that I can't do justice to here, but let's try. So our general concern is to write down a probability distribution for lots of variables, right? So let's do a very simple case. Let's imagine that the variables Si are just plus and minus 1. And they might, for example, represent, if you were really thinking about physics, you might think, well, this is a magnet, and Si equals plus 1 means spin up, and Si equals minus 1 means spin down. But it could also be that you're looking at a small region in space, and Si equals plus 1 means that there's a molecule in the little box, and Si equals minus 1 means no molecule in the box. Or it means that some organism lives in this small patch of space or does not live in this small patch of space. There are obviously lots of examples that you can think about. And what I'm going to do is to imagine, to give us an example where we can actually calculate everything. Let me imagine that I equals 1 to up to n, they live on a line. So 1, 2. Okay? And so what's going to happen is that at position 1, I might have a plus 1. At position 2, I might also have a plus 1. At position 3, I might have a minus 1, plus 1, minus 1, plus 1, plus 1, minus 1, plus 1, minus 1. I don't know, it keeps going, right? And now I want to write down what's the probability that you'll find all of these things in this particular arrangement. So for example, just to keep thinking about, there are many different examples of this, right? These could also be, this axis could be time, and the state +1 could correspond to an animal doing one kind of behavior and the -1 doing a different kind of behavior. So I'm just keeping track of what the animal is doing at each instant in time. And I want to write down the probability, and let me do something, again, quite simple. Let me suppose that the probability, again, can be written in an exponential form. And you might guess that there's some bias. So, for example, if this is animal behavior, the two different behaviors might not be equivalent to each other. So there's some bias to do one rather than the other. Well, how do I express that? What it means is that when S is +1, the probability is different than S is -1, and that's true at every point. And remember, probabilities multiply, right? So in the exponential, they should add. So what I'm going to do is I'm going to put a constant A which in the exponential, which multiplies every single S sub I. And if I stop there and close the parenthesis, then what I've described is a model in which at every moment in time along this axis, you flip a biased coin, right? So the probability that you come up is proportional to e to the +a. The probability that you come down is proportional to e to the -a. So there needs to be some coefficient out in front to normalize everything. But if I stopped here, it's just independent choices at every bin, right? So what's the simplest possibility beyond this? It's that what I do at this moment depends on what happened here. And since there's only pluses and there's only two choices, then basically the question is, do I do the same thing or do I do a different thing? So if I want to write down something that biases me either to do the same thing or to do a different thing. So the way I do it is I put another constant. And I'm going to stop there. And I multiply, I just write, if I take SI times SI +1, since I've chosen them to be plus and -1, if they're the same, the product always comes out to be +1. And if they're different, the product comes out to be -1. So I'm just counting, do I do the same thing or a different thing? Okay, again, so for the physicists in the audience, this is the one-dimensionalizing model with nearest neighbor interactions. For everybody else, that doesn't matter, right? I'm describing a walk along a line, and at every moment I have two choices. There's a bias, one's more likely than the other, and I have a little memory from one step to the next that I either tend to do the same thing or the opposite. And you could imagine making things more and more complicated, but let me stop here. You might say, well, if you stop, yes?
So you have only one direction?
Simple case, yes. Just everything's on a line.
You always go from I minus I.
Yes, but you'll notice that since you sum over all the terms, I could rewrite it as I times I minus 1, j times j minus 1.
Yeah, what I mean is like it's bring a memory, it's not like speed.
If you sum all the terms, then you can't tell whether I said it as if I was going this way, but really, since I'm just counting the products, I'm just asking whether at this boundary, are these two the same or not? And I can't tell whether it's going this way or that way. Right. If you want to write down something that keeps track of the direction, you need triplets. Two won't do it, right? So you might say, well, this model is already so simple that you don't need to simplify any further. And you sort of be right. But it's precisely because it's so simple that we can do everything that it's useful as an exercise. So how do I I imagine I wanted to do something that was as grand as going from molecular dynamics to fluid mechanics. How do I do it? Well, I make a little box, and I look at all the molecules inside the box, and I somehow average over them and pull out a variable which is the velocity of that box and the density in that box, and maybe I might need to keep track of the pressure or something else. Anyhow, so I look locally, I average things together, and I pull out a variable that I think is the sensible variable to keep track of. And then I want to ask, how do those variables behave? So what's great about this model is you can do this exactly. So let me give you an example of how to do it. So suppose you say, well, and an important part of this is to realize that these parameters A and B, they're defined on the scale of the individual elements, right? So A really is the bias between the two different possibilities at each site in space or at each moment in time. And B really is the bias toward being similar or different at the scale of one step. When you say, look, one step is very short, I'm not interested in that. I want to zoom out. But it would be useful if when I zoomed out, I got variables that kind of look the same as the variables I started with. So I'm going to give you a strategy for doing that. So let me take a box and put it around 3 of these variables. And since I'm keeping track of a kind of heads versus tails variable, the natural thing to do is to say, well, do majority rule. So in this group of 3, I'm going to say that it's +1, because 2 of them are +1 and 1 of them is -1. So you can think of that as averaging and kind of rounding off, or you can think of it as majority rule. At this scale, it doesn't make any difference. So it's something like taking all the molecules in the box and averaging them together to get some property of the fluid. Here, it's also +1. Here, it's also +1, which shows you that my choices weren't really very good when I drew the picture in the first place. I should have been thinking more carefully. So the idea is that I have variables Si on the smallest scale. And then I have, if you want, Si tilde on the scale which is 3 times larger. And the rule is very simple. Si tilde is you take the sum let's say you take 3i plus 1, and 3i minus 1, and then you take a step function. So sorry, you just take the algebraic sign. Okay? So why is it 3i? Well, it's because I write this guy to here is 3 steps, right? So I keep counting by 3s. And then I take the guy to my right and the guy to my left. I average them all together. If the outcome is positive, I call it +1. If the outcome is negative, I call it -1.
It's the same?
Sorry, S, sorry. Some of you will know why I made that mistake, but I'll try to be consistent. Okay? So now what I want to do is to write down the probability distribution for these variables. Now, clearly this is just algebra, right? Because I gave you the probability distribution for the S's, and the S tildes are related to the S's. So if I do all the algebra, I should be able to figure out what the probability distribution is. Okay? And I invite you to do the algebra. It's not that hard. But actually, an important part of this problem is that without doing the algebra, you can get the form of the answer. And the thing you have to realize is that if I tell you S tilde at this site, I'm telling you something about these three variables, right? I'm telling you, let's say, that they're 2 up and 1 down inside this box. I don't know how they're arranged. And if I tell you the value of S tilde at this site, if I tell you it's +1, then I know that there's two +1s and 1 -1, but I don't know how they're arranged. The question is, in the probability distribution, is there a term that connects this box to this box? And the answer is no, because every site is only connected to its neighbor. And so the only dependence of this on this is through what's happening in this box. So that means that this box and this box are conditionally independent if you know the thing in the middle. So that means that when you write down the probability distribution, the only things that can appear explicitly are things that connect the neighboring boxes. Because when I started, I only had connections between neighboring sites. And I can't jump, right? That was the model I started with. So if you go through all the algebra, you will discover well, let's think for a moment. If there's a bias between being +1 and being -1, then there'll also be a bias for the majority being +1 and -1. So there will be a term which I can call A tilde, which looks like this. And there'll be some coupling between what happens in one box and the neighboring box. And what that means is that if you go through all the algebra, and as I say, it's not that hard, but something to do in private. What you discover is that the model that you get back looks the same as the model that you started with, except that when you change scale, A and B go into A tilde and B tilde. Okay. Yes. Thank you. Okay. Yes.
I don't know if I didn't understand the notation, but it seems to me that when you make the SI equals sign of
Yeah.
there's an overlap of the boxes, right? Because if I change from I to I plus 1, then the last 2 spins will be inside the next box, right?
Well, the way I did this, you have to be careful of the counting, and let me see if I did it correctly. So for example, if I choose I equals 1, then this is 3, 4, and 2, right? If I choose I equals 2, then this is 6, 5, and 7. So they don't overlap, right?
What's the in this I don't know if 3i plus 1.
So this is 3i plus 1, and 3i minus 1. Okay? So that was an attempt to do this very quickly, and fortunately it actually worked, but thank you for checking. Okay? So what I want to emphasize here is that this is a problem in which I write down a model of what's happening at the shortest possible distance, or the shortest possible time. And I say, look, I don't care what happens one step at a time. What I'm going to do is I'm going to average out what's happening on a scale of order 3 times the smallest thing. And then ask, okay, I get new variables on this bigger scale, so it is as if you put on glasses that blur your view, right? So you can't see all the fine scale stuff, or alternatively, you take a step backward. And so the things that you could just barely see have stop being resolved. And when I take a step backward, I get a new description of the world. But that description actually has the same form, just with different coefficients. Okay. That means you could keep doing this. And as I zoom further and further out in distance, every time by a factor of 3, the constant A and B gets changed. And so there's some mapping for what happens to A and B every time I change scale. Okay? And the question is, what's going to happen? So this model, precisely because it's so simple I can calculate everything, is also very boring. Because it has the property that when B goes to B tilde, it gets smaller. And it keeps getting smaller as I keep doing this. And what that tells you is that no matter where you started, if you zoom out far enough, B will eventually go to 0. And so indeed, although this model is very simple, I can simplify it. Because if I only care about things on very long scales, actually I didn't even need to write down this term. I could have just kept this term, it would be okay. So this is the beginning of a very big idea, which is that you can take, you have a model, and your model lives inside a family of models. And this family of models is specified by parameters. And let me do the thing that physicists always do and call them G. So there's a whole collection of them.
Sorry.
Yes?
That's
Oh, belongs to, right? Right.
no,
It's okay.
no, the other one.
Okay.
Family?
Of?
Ah, okay, it's just an F.
Oh, it's this one that you couldn't read. I see. Yeah. The funny mathematical symbol was okay, but it's true, if all the F's looked the same, it might help. Right, good. Is that better? Strangely, the G's all look the same, but the F's don't. So F and G are not interchangeable. So I have a model, and let me assume for the moment that this model lives in some space where I can think about things being next to each other. They're next to each other in time, they're next to each other in physical space. And now I go through this exercise of averaging out the things on the shortest distance. Right? So these parameters are defined on the shortest scale, which I could call A. And now the idea is that I'm going to average out details on scales shorter than L. And let me emphasize that since we're talking about probabilistic models, average out means exactly that, right? Remember that when you go from +1, +1, -1 to telling in the box it's +1, what that means is that if I want the probability of there being 1, I should look at the probability of all the different ways of putting 2 pluses and 1 minus inside this box. So I take the probability for the whole complicated state of the system, and I literally add up all the possibilities that leave exactly 2 +1s and 1 -1 inside this box. So I am actually averaging out the things that happen on the shortest scale. So it's not average out in some vague, hand-wavy sense, right? It's probabilities. You add up all the things that are left invariant if I just tell you this number. So what's going to happen? In this simple case, right, I had a model that had only 2 parameters, and amazingly enough, when I do this, I get a model with 2 parameters, and the 2 parameters kind of mean the same thing, they just have different values. In general, that won't work. If you start with a model that has just a couple of parameters and you go through one of these steps of averaging out all the short distance things, you'll get more terms in your model. And the easiest way to see this is if instead of doing this in a line, we did it in a square. And then you would see that if you tried to average out blocks, then the blocks can couple to each other in complicated ways. And it's a nightmare. But if you imagine that you started with lots and lots of, you started, in some sense, let yourself think, oh, the model I started with maybe wasn't complicated enough. Let me imagine putting in more terms. Well, now, the more terms I put in at the short scale, the better chance I have that when I go through one of these steps, I get back a model in the same form, right? I don't get any more new terms. So what I should do is to imagine that this space of models is very big, has lots of parameters, and I start at the short distance, and I don't know exactly what the values of the parameters are, but I now watch them as I zoom out and change my scale. And what's going to happen? Well, in general, there are many parameters. So here's G17, and here's G32. And what can happen? Well, one possibility is very boring, which is that these parameters just flow to 0. So what am I drawing? I'm drawing what happens to the value of this parameter as I zoom out in scale. So I should think now about how these things depend on L. And it's possible that as L increases, they just go to 0. L is the scale over which you've averaged everything. So here, L is 3, or 3 times A. Well, A is 1, to keep things simple, and L is 3. But you can imagine zooming out. And in fact, it's convenient to think of doing this continuously, although in many cases you have to do it discretely. Okay? There's another possibility, which is that at least some parameter, or some parameters, that as you zoom out, they just get bigger and bigger and bigger. And what would that mean? Well, let's think about, imagine that happened in this model. So if A got larger, what would that mean? It would mean that the bias between one state and the other got stronger and stronger. And so if you zoom all the way out, it would look as if everything was always +1 or -1. Or if this got stronger, then it would mean that everybody was exactly like their neighbor. And so it would look, you might not know whether it's going to be all +1s or all -1s, but you know they'll all be the same. Okay?
Well, that the blocks of continuous values would be larger, not all the same.
Well, but if this really flowed to infinity, then they'd all be the same, right? So just to, okay. So now, let's see if I can do this a little better. I could imagine that there are separatrices right? And that this flow, and this is a flow through the space of models, right? And if you want, it's like in dynamical systems, right? But the time here is your zooming factor. And so time flows forward as you zoom outward. And so you can, like with all dynamical systems, right? Then in the state space of the dynamical system is the space of models. And you have all the phenomena that you expect to see in dynamical systems, right? You have fixed points. Fixed points can be stable or unstable. There are separatrices, and so on. Okay. So these different possibilities get names. And so I've made it simple here because I'm just in 2 dimensions. But so because I'm in 2 dimensions, these things have special names. So here, you might say, well, there's a weak coupling fixed point. So fixed point, just like in dynamical systems, right? You flow there as time goes to infinity or the scale zooms out infinitely far. And it's weak coupling because these constants that appear in the probability distribution have gone to 0. Somewhere out here, there might be a strong coupling fixed point. Somewhere. And then there's something here which is stable, which is a saddle, right? It's stable in some directions and unstable in others. And this is called a critical point. But more generally, what you realize is that as L goes to infinity, some of the Gn will go to 0. And the amazing thing is that if you start doing this for more and more models, it's not some, it's most of the Gn go to 0. So most of the things that you might try putting in the model that you started with, if you zoom out far enough, they just go away. Of course, they leave their imprint because the dynamics in this multidimensional space is not trivial, right? So one of the parameters is going to 0, one of the coordinates is going to 0, but along the way it pushes the other coordinates around. And so the parameters that describe the system on a large scale are not, it's not like you can just zero out the parameters on the shortest scale and say, okay, I'm done. No, all the parameters that are left get moved around, but the form of the model gets much simpler because most of the coefficients have gone to 0. So this is why, so these things, for technical reasons, they are called irrelevant. And one of the things that I love about this field is that the word irrelevant has a technical meaning. We often write down models and we say, oh, I'm going to leave that out because it's irrelevant. No, but if you could actually do this calculation, irrelevant means something very specific. And if you can show that it's irrelevant, you're not leaving it out because it's your opinion that it doesn't matter, right? You're leaving it out because even if you put it in, it would go away. It's pretty amazing, right? Okay, so this is a description of what happens in the space of models. And it relies very specifically on the fact that they live, the models, the variables inside the model live in some space where you can talk about the things that are next to each other. And so when you say average out all the details on scale L, you really mean, you know, in that space, look over a distance L and average those things out. Okay, it might be time, and so so the units of L might be complicated. It might be that there's some network, and L is how many neighbors, the radius of neighbors. It doesn't have to just be, you know, d-dimensional space, but there's a notion of neighborhood. For a lot of biological systems where we have many variables, we don't really have a notion of neighborhood. So for instance, if you think about neurons in the brain, you realize that neurons are big objects, right? They have a reach where they collect inputs from other neurons, which is a noticeable fraction of a millimeter. Even though the cell body is measured in microns, and the next neuron over is only a few microns away, the neuron has a tree coming out of it which reaches for 300 microns. And so that means that two neurons are next to each other, but that doesn't mean that they only talk to the guy who's next to them. The neurons can actually reach hundreds of neurons across, right? So neighborhood doesn't mean so much in a network of neurons. And if you thought about a genetic network, then neighborhood is also very complicated, right? Because what it means for things to interact. Yes?
What can you say about phase? I mean, if I change the notion of where a neighborhood starts, it would change all the values. Does that impact in any way?
So, at this point, what I want to do is to be sure you understand what happens in the cases that we understand. And then we need to make a list of all the things that are going to be a problem if we try to go to the cases that we care about. Okay? So I just gave you one, which is that neighborhood isn't so easy to define in biological contexts. Another one is related to what you're asking about, which is that this all makes sense. You'll notice that every point is equivalent to every other point. So there's a kind of homogeneity. So what happens if the system is heterogeneous? So because of the homogeneity, the answer to your question in this case is no, you don't need to worry about it. But if it weren't homogeneous, then the answer would be yes, at least in detail. But, so we need to worry. So problems are what you might think of as non-locality. So I don't have a notion of neighborhood. There's a problem of heterogeneity. There are probably more, but there's a really big one, which is what if you don't know the model? Right? So this discussion all works if I know where to start. So if I start here, I can go through all this machinery and classify. This term is irrelevant. The opposite of irrelevant, of course, is relevant, so that's a term that I have to keep. And I can classify them inside the model or inside the family of models, and everything is wonderful, okay? And then I understand that if I'm trying to describe things on a large scale, I don't need to hold on to the irrelevant terms. I only keep the relevant terms. There aren't too many of them, and so I know what model I should write down, or more precisely, from the family of models that I started with, I can collapse to a much smaller family of models. By the way, that collapse means two things, right? One is that if I only ask questions about things on a large scale, it's simpler because the family of models is smaller, there are fewer parameters, but also it's more universal because there are many different microscopic models that all flow toward the same set of macroscopic models. So that's the fluid mechanics of water and alcohol are the same, despite the fact that the molecular interactions are different. Okay? Yeah.
What do you mean by neighborhood? Because why I find the problem that our model, the neighborhood is simple to watch what's the neighborhood. But on a base transition, for example, the interactions are larger. It's not on the
So sorry, let me give the short answer for you, which is no. At a phase transition, the correlations extend over long distances, but the interactions are still short distances, right? That's the magic, right? Is that atoms only interact with their neighbors, and yet you grow correlations over a very long length scale. Okay.
neighborhood for us now is only the
Well, so neighborhood is the explicit dependencies that appear in the probability distribution. So this is the problem of using intuitions from physics in other contexts. So there's a right, as I tried to emphasize to you, statistical mechanics is the earliest successful example of of non-trivial probabilistic models. And so we use probabilistic models in lots of contexts, but in some way this is foundational, right? But when you write down things in statistical mechanics, the terms have very specific meaning in relation to what's happening in the physics context that they started in. And it's tempting to lapse into that language. So for example, we would say in physics language that this is the coupling between the variables that live at site I and site I plus 1. But you could also just say, wait a minute, I'm talking about probability distributions. This is about dependencies. And the issue of locality is a question about, if you want, cluster decomposition or something, right? It's about there are these things called Markov blankets, right? How big a region, if I look at one variable, how big a region do I need to look at in order to find all of the explicit dependencies, right? So that if I draw a circle that's big enough, then the guy who lives in the middle of the circle is conditionally independent of everything outside the circle. That's what locality means. Now, again, in physics we think, okay, they're particles, they interact with each other, we have some very specific thing in mind, but from the point of view of probability distributions, there's a well-defined notion of locality. Doesn't have anything to do with that. You can jettison all of that physics language. However, you might not have a system in which neighborhood is very well defined. There's problems with heterogeneity, but the most important thing is I want to be able to do this not for models. I want to be able to do it for a real thing that's sitting in front of me, and maybe I don't know what the model is yet. In fact, my hope is that by going through an exercise like this, I don't have to write down the microscopic model with a zillion parameters in it. I can get some idea of what the simpler model is that I end up with, right? But I don't know in advance what this model is, so what do I do? Well, along the complicated path that these ideas took, people tried to test them by doing Monte Carlo simulations of models like this. And if you think about it, the problem of analyzing those Monte Carlo simulations is not unlike the problem that we face if we look at real observations on a biological system. We get what happens in a Monte Carlo simulation. You draw samples out of the probability distribution. So somebody shows you a configuration of plus and minus ones. And then they show you another one, and then they show you another one, and then they show you another one. So for example, if plus 1 is a neuron is active, and minus 1 is a neuron is silent, you could imagine that somebody's figured out how to record from a large number of neurons, and they give you a snapshot. At this moment, neuron number 1 is active, neuron number 2 is silent, and so on. And then one time step later, they give you another snapshot, and another snapshot, and another snapshot. And that looks exactly like the output from a Monte Carlo simulation. So if I gave you the output from a Monte Carlo simulation, or real data, what would you do in order to use these ideas to search for some kind of simplification? What you would do is you would actually coarse grain the data instead of coarse graining the model. And so what would happen? Well, if you're coarse graining and the variables that are left are becoming more and more independent of each other as you get to longer and longer distances, like in this problem, where b is going to 0 as you get to longer and longer distances, then if you're really averaging, then you're averaging together things that are more and more independent of one another. And that means that you're getting closer and closer to the conditions under which the central limit theorem is true. And so if I look at the probability distribution of these coarse-grained variables, don't do majority rule. Actually average them together, okay? So do the averaging part, but not the algebraic sign. If they get more and more independent of each other, then the distribution should become more and more Gaussian. On the other hand, if they become very strongly coupled so that they all have to have the same value, then the probability distribution is going to start to look like it has multiple peaks that are well separated from each other. And then it's possible that something happens in the middle. So in fact, if you follow the probability distribution of the coarse-grained variables, and you flow along one of these trajectories, if you go this way, then the distribution should end up with right? The couplings are getting stronger and stronger, and so the distribution should end up being bimodal or multimodal, right? Because you don't know, this strong coupling just means all the variables are the same, doesn't tell you what the value is. On the other hand, if you flow this way, all the couplings are getting weak, and so the variables are becoming more and more independent of each other, and you should end up at a Gaussian distribution. And then if for some reason you're able to track along here, something special might happen, and you notice that if you actually hit this point, although it's unstable, it is a fixed point. And so that means that there's a probability distribution here that will look the same as you do the coarse graining. In the same way that the probability distribution here is Gaussian and looks the same when you do coarse graining, and the probability distribution out, I mean, it changes the variance, but you should normalize that away. So the idea is that if you look at data, if you follow the distribution of the coarse-grained variables, it should get simpler. So there are possibilities like it just becomes Gaussian, which means that you've gotten to some scale which is big enough that now all the variables are independent of each other. Or alternatively, you get something bimodal, which tells you that all these complicated interactions that you started with, what they do is they just cause the whole system to all be in one state or another state. So you get the emergence of some sort of switch-like behavior for the system as a whole. Or you could get what's called a non-trivial fixed point. And at this point, I should tell you that there was a marvelous essay which appeared in Physics Today, which explained that in physics, we should banish the use of the word trivial. Because the only purpose that trivial serves is to make students feel bad, right? This is the trivial solution. And you're sitting there saying, I have absolutely no idea. I don't even see that this is a solution, let alone that somehow it's not the interesting one that I'm supposed to pay attention to. And while you're thinking about that, the guy's gone on to talk about something else, right? So non-trivial is just that Gaussian is very old, and so it's not interesting, right? So non-trivial really means non-Gaussian. Okay. So that's also complicated, right? Because you know that the act of coarse graining is exactly the thing that you do when you're trying to understand how the central limit theorem works, right? What am I doing when I coarse grain? I'm taking the things in this region in space and this region in space and averaging them together. That's the thing that I usually do in order to understand how the central limit theorem works, right? I keep adding random variables together and things become more and more Gaussian. And here, somehow there's the possibility that when you average things together, you go towards something, but not a Gaussian. Well, except that, so maybe calling this simpler, well, it's simpler in the sense that when you started, the distribution could have had any shape, right? In particular, right, if the variables that you start with are binary, plus and minus 1, then when you average a few of them together, you get a few different discrete values. And then by the time you average many of them together, it's almost continuous, but there's no reason why the distribution should have any particular shape. You could have anything, right? But if you keep going, Eventually you get to something, you get to one of a finite set of possibilities. So,
But you don't know the one that is no Gaussian.
well, that's the most interesting one, but the other possibilities are, the other ones are trivial, yes. Okay, let me also make an observation, which is that this non-trivial fixed point, which lives here, there's a problem with this, right, which is that this is an entirely mathematical description, and it's supposed to come not from mathematics, but from physics. So what does this picture have to do with physics? So since I'm interested not so much in the physics, but in how I can use this to think about a biological system, let me just tell you the answer. If couplings are weak, that is as if the interactions between all the particles weren't very strong. But what sets the scale for interactions between particles? The temperature. So if the interactions are weak, that's the same as the temperature being very high. So this is a fixed point that corresponds to what happens if you warm the system up very far, which means that you destroy all the order. The solid melts into a liquid, which becomes a gas, right? So whatever order, it stops being a magnet. Whatever ordering you thought you had, it goes away. This is the opposite. This is the one where all those interactions become very strong. But strong compared to what? Again, strong compared to the temperature. So the way to be strong compared to the temperature is to send the temperature to 0. So this is the low temperature fixed point. And as you all know, between low temperatures and high temperatures, most materials undergo phase transitions. And under certain conditions, that transition is described by what's called a critical point. And that's what this is. So what's astonishing in this is that you can make a mapping between the behaviors in this very abstract space and the behavior in the phase diagram of real materials. And because this is a special point, you can understand the dynamics of these flows in this neighborhood without knowing anything about where you started. Right? So imagine you go to this point and you study what happened, just like when you do dynamical systems, right? Global things are very hard. Local things are much easier. So I can go to this point and I can study the behavior in the neighborhood of the point and understand everything, except, of course, where I started in order to get here. That's how much harder. But since I know that this point corresponds to particular points in the phase diagram of the real material, how you set the temperature and the pressure and the magnetic field and so on, I have a theory of what happens in the neighborhood of those points in the phase diagram that's determined entirely by the mathematics in the neighborhood of this point. Okay? And I can forget about all of the microscopic things about where I started in order to get here. Okay? And that theory works to many decimal places, which is quite astonishing. Okay, so more than half an hour, but okay. So what this says is that if you want to find out whether this picture tells, if I give you the configurations of a real system, and I want to find out whether these ideas are useful or not, what I should do is actually go through the exercise of coarse graining and follow the probability distributions. And furthermore, if you think about the example of the Gaussian, which you understand because that's the central limit theorem, you know that along the way toward becoming Gaussian, certain things exhibit simple scaling behaviors. So for example, if you average together n variables, and you're approaching a Gaussian because they're almost independent of each other, then the variance will go down as 1 over n, right? So associated with the flow toward particular probability distributions is scaling behavior along the trajectory. And what's interesting about the non-Gaussian fixed points is that they have scaling behavior which is not described by simple powers. So instead of going like 1 over n, it'll go like 1 over n to the 0.783. Okay? And you can actually relate that to the dynamics of the flows in the neighborhood of this point. Okay? So, if I think that all of this apparatus is going to help us to simplify the behavior of real biological systems, the question I should ask myself is, can I actually do this coarse graining exercise and see the emergence of see the convergence toward probability distributions that have a fixed form, and do I see scaling along the way? Okay? So that's the idea. Now, what I'm going to tell you is that we have gotten as far as showing the things that I just said, but we don't know what the theory is that describes where everything is headed, okay? So it's a progress report. Let me emphasize that if you found that you were flowing towards something Gaussian, then in some sense you would have failed, because what that would mean is that as you average things together, you get to some scale, and at that point they become independent of each other. And so yes, if you want to look at scales which are much longer than that, everything is simple, but you've also thrown out, as we say in American slang, the baby with the bathwater, right? You've missed all the interesting stuff. All the interesting stuff happened before they became independent, right? And if it flows toward being bimodal, and that means the whole system is kind of locking up into some very strongly ordered state, which also seems a little weird, it's probably the fluctuations around that state that are interesting. But nonetheless, it would be true that you would have seen some form of simplification. So let's see what happens. So what's the example that we tried? We have the good fortune that next to us there are experimentalists who have really pushed the technology for recording from large numbers of neurons simultaneously. So the idea is going to be that the SI is going to be that neuron I is active, +1, or silent, which will be 0 for reasons that you'll see in a moment. Not +1 and -1, but +1 and 0. It's a little simpler. So how do you measure this? Well, there's two ways to measure, there are now two different ways to measure the electrical activity of neurons. One is with a wire, right? It's electrical activity, so currents are flowing in and out of the neuron, so you stick a wire very close to the neuron, and some of the current shows up at your wire, and you amplify it, and you measure the activity of the neuron. You can also put the electrode inside the cell, you can try to attach it to the cell. So there's a whole set of tools that directly try to observe the electrical signal. These technologies are improving, but there's a challenge, which is that in order to monitor many neurons at the same time, you have to stick in many wires. And you might be nervous about sticking lots of wires into the brain. An alternative, so good news is you're actually measuring the electrical signal. You can do it with very high ratio, high time. The alternative, bad news is you're turning the brain into a pincushion. Not so good. Getting better, okay? People are using soft electrodes and, okay. So an alternative emerged, which came with genetically encoded fluorescent proteins. So I figure most of you have probably heard about the green fluorescent protein, right? So people engineered, they then started, after the discovery of the green fluorescent protein, what people did was they started to engineer versions of this protein which would respond to different signals inside the cell. So what you really like is a version of the green fluorescent protein that inserts itself into the cell membrane and responds to the voltage across the membrane. And then it would be just like using an electrode, except that the signal would show up not in the wire that you stuck in, but in the fluorescence. And so you could look with a microscope and see how active the neuron was. You can do that, but at the moment, those molecules are not so good, and so the signal-to-noise ratio is not so high. The alternative is that when neurons are electrically active, a consequence of the changing voltages is that calcium flows in and out of the cell. And when neurons are more active, the calcium concentration inside is higher. So what you do is you genetically engineer a version of green fluorescent protein which is sensitive to the ambient calcium concentration. And so when the calcium concentration goes up, the fluorescence goes up. And remember, the reason that green fluorescent protein was so surprising, right, is that there are lots of molecules in your body that are fluorescent, but most of them are not fluorescent because of the protein alone. It's usually because of some complicated cofactors, right? The same, so for example, if you think about the fact that your blood is red, right, that's not because of the protein, that's because of the heme, a rather large organic molecule that cells have to synthesize. And so in order to convince a cell to make a molecule that was fluorescent, if it had a cofactor, it had one of these big organic things hanging off the end of it, you'd have to give the cell all of the apparatus to make that cofactor and hope that it all pieced itself together in the right way. Very complicated. So the wonder of the green fluorescent protein is it really is just a protein. It's a polymer of amino acids. So you put that gene into the organism, and it makes something that fluoresces. So you put this into a mouse, and if you want to be fancy about it, you should put it under the control of regulatory elements which turn on inside neurons and not everything else, so that the entire mouse doesn't glow green. And if you're really sophisticated, you could put it under the control of regulatory elements that turn on inside one class of neurons and not another, so you could listen in only on certain populations of neurons, okay? So our colleagues have done this, well, they've done it in many different systems, but in particular, they've done it in the hippocampus of a mouse. So the hippocampus is a region of the brain which is involved in navigation. If you look in that region of the brain, you find the famous place cells, which have the property that if the mouse is running around, then when it crosses a particular point in space, the neurons become active and then they turn off for the rest of the time. So the neurons seem to encode that particular place in the world. It's more complicated than that, of course, but that's the sort of first order description. And the technology now is, so so what I've told you is if I can get the mouse to express a fluorescent protein whose fluorescence is sensitive to calcium concentration, then if I look with a microscope, I can measure the fluorescence of a single cell, coming from a single cell, and I know how active that neuron is. There's a problem, which is that neurons are small, and you'd like to be able to see individual neurons, which means not only that you have to be able to resolve individual neurons, you have to be able to separate them from their neighbors. And they're densely packed. So your resolution needs to be even better than the size of the neurons. It needs to be the size of the spaces in between, right? There are many regions of the brain in which nothing interesting happens if the animal is standing still. Amazingly enough, the region of your brain devoted to navigation is one of those. So if you just stand there, nothing much happens. In fact, in the experiment where the mouse runs around and the place cells turn on, if you pick up the mouse and move him around, the place cells don't turn on. He has to get there himself, okay? There's some possibility that if he sits and imagines going there, it might also those cells might also turn on, but it's hard to ask the mouse what he was imagining. So there's a lot of controversy that surrounds those experiments. So the challenge experimentally is you'd like to do very high resolution microscopy, but you'd like to do it in an animal that's running around. Those don't go together so well. So one solution, which my colleague David Tank adopted, is you build virtual reality for the mouse. So the mouse is sitting with his head held fixed so that the brain isn't moving around and you can look inside with your very high resolution microscope. We'll discuss the microscope in just a moment. But he's standing on a styrofoam ball and you have a column of air that holds the styrofoam ball up. And now he can run on the styrofoam ball. And then you monitor the rotation of the ball to figure out where he would have gone if he were running on the ground. And you send that to the computer to drive virtual reality. So the mouse thinks he's running around. So you have to get the genetic engineering right to make sure the molecules are all in the right places. You have to build this virtual reality setup. Then you have to build a microscope which is of sufficient resolution that you can look deep inside the brain and measure the fluorescence with submicron resolution. Okay? It's amazing this experiment works. You have to, I mean, the microscope that you use is, you know, it's driven with a high-powered laser and everything, right? So the result is you walk into the lab, it looks like a laser physics lab, okay? Except somewhere in there's a little mouse on the styrofoam ball, okay? So, so the result is, okay, I wanted to emphasize how hard these experiments are. They're really extraordinary. The end result is that for each neuron, I, you get a signal, which is essentially a fluorescence signal. And it looks like this. And it really does look like this in that the noise level is on the scale that I'm drawing it. And so you can do two things. You can either take, so you can agree that this is 0. And you can either say this is 1 and the rest are 0, or you can keep track of the analog value of the fluorescence, which is presumably related to the calcium concentration. Take your pick, okay? So these are the variables that we're going to try coarse graining. But I told you I had one more problem. I'll stop in just a couple minutes. Which was we didn't have a notion of locality. I don't know what neighborhood means. I can't use the fact that two cells are next to each other because they interact over long distances. What I can use is the idea that if I go back to this problem and I scrambled the list of variables so you didn't know who was next to each other anymore, there is a way you could figure it out, which is that the guys who are most correlated with each other are next to each other. Right? If you watch them, next time you look, this guy might be up, this guy might be down. But if you watch over a long time, or if you see many, many configurations, if you look for the things that are strongly correlated, they're the ones that are close together. So what we can do is to use as a notion of neighborhood the correlations themselves. So I can define I can define a covariance matrix, and I can define a correlation matrix, which is Cij divided by the normalized, so that I'm computing correlations rather than covariance, right? And I can say, well, if I see two neurons that are very strongly correlated with each other, those are the two cells that I'm going to average together. So what I'm going to do is I'm going to take, well, I could do active, not active, or I could do xi equals the fluorescence signal. Right? So this one is the easier one, so let me do that one. So what I can do is to say I find I and j, which are the maximum, I not equal to j, which are the maximum in Cij tilde. And then I construct xi, which is xi plus xj. And then I keep doing this, right? Then find the next most correlated. And when you're done, you now, if you started with n variables, I now have n over 2 variables, xi tilde. Right? Yes?
This is like some sort of greedy algorithm, right? They take the two with the highest and then they merge those and then they take the next two. Why? Because you have a covariance spin, right? So why doesn't you just do PCA and average those like such that you didn't let the number of groups be free?
This description of how you do coarse graining, this is in the jargon referred to as the real space for normalization group. The alternative is you take the variables, you Fourier transform them, and you put a cutoff, you average over all the things at short wavelengths or high wave vectors. That's called momentum space normalization group. What I'm describing to you is the analog of the real space calculation. There is an analog of the momentum space calculation which indeed uses PCA rather than the, and everything also works there too. So it's just to, so if you want, at this stage, I've gone from describing things at the scale of single neurons to describing things at the scale of 2 neurons. If I do it again, I can describe things at the scale of 4 neurons, right? My variable xi now describes the average behavior of 4 neurons instead of 2 neurons, and so on. And so I can keep doing this, right? I can do it at different values of k. And these experiments are remarkable because n is bigger than 1,000. So I can do this over a wide range of k's. So there's a problem, which is that the x here has a slightly funny distribution, right? There's a real 0, and then there are these transients. So when I average variables together, I should be careful. I want to preserve what 0 means, because that really means the neuron is silent. But then what do I do about the scale when I average things together? So what I'm going to do is I'm going to normalize things after I average together. I'm going to normalize things so that if it's not equal to 0, on average it's equal to 1. Okay? Just to set the height variable. The height variable here doesn't really mean anything, right? Because it has to do with how neural activity gets transformed into calcium concentration and how that gets transformed into fluorescence. Those aren't really interesting to me. So I go through this exercise of coarse graining and normalizing. What happens? Well, I told you that we should keep track of the probability distribution of the coarse grain variable, and we're going to do it on scale k, right? Here. And we know that there's some probability that the variable will be really 0. So there'll be a delta function, and it will have a weight. Okay. And then there'll be some term which is the distribution of the non-zero values. So the astonishing thing is that as you do this, if you look at fk, then as you increase k, what happens is that the probability distribution looks more and more like just a simple exponential. So you keep averaging together all these variables, and you get back something that looks more and more like an exponential distribution. And by the time you've averaged together 16 variables or 32 variables, things are hardly changing at all. You're getting a little bit of motion in the tail. But over decades in probability, you see almost no change at all. So you're seeing the convergence of the distribution toward a fixed form, but not a Gaussian. Let me remind you that if you take 2 variables which are individually exponentially distributed, but independent of each other, and average them together, you don't get back an exponential distribution. In fact, you get something which goes to 0 at x equals 0. And you don't see this here. Okay? So there's something about the underlying correlation structure which is allowing the system to approach this fixed point, which is not one of the simple ones. What about scaling along the way? Well, there are many things you can check, but time is short, so let me tell you one thing you can check. Sorry, I should have been more precise, right? If the weight here is W, the weight here is 1 minus W. It's this part that's interesting. What about the form of WK? If all the neurons were independent of each other, I mean, WK is the probability that when I put K neurons together, they're all silent. So if they were independent of each other, you'd say that you should just multiply the probabilities of each of them. And correspondingly, as K gets larger, the WK should go down exponentially. So you might expect that WK would look like e to the minus a times K. And it turns out that's not true. Instead, there's a number here, which is an exponent of k, which is not equal to 1. But the fit is essentially perfect over 2 decades in k. And this number, instead of being 1, is something like 0.88, plus or minus 0.02, I think. The fit is so good that you can determine this value to the 2nd decimal place. Furthermore, you can do the experiment in 3 different mice, and you get the same answer to the 2nd decimal place. Remember, I told you that things are not only supposed to simplify, they're also supposed to become more universal. So here you see a scaling behavior which is the same in different instantiations of the same network in different animals. Okay. So there'll be time, right? We'll have a break, but let me try to summarize so you know what it is we should be talking about when we come back after the break, although maybe you're confused about other things. I gave you a very long introduction and then a little bit at the end about real biology. The reason is that what I wanted to convince you of is that there's this enormous theoretical apparatus out there that we have in physics, which tells us that there's a real strategy for finding simplification in a systematic way by using coarse graining. That our description of macroscopic behaviors should be simpler and more universal than our description of microscopic behaviors, and that is not just a hope, it's something that we can really implement. We usually implement it in the context of models, because we know how to do the calculations. But our experience with Monte Carlo simulations tells us that we can at least try to do it in the context of data without even really knowing what model we're talking about. And what astonished us is that the first time we tried this in the context of a real network of neurons, we saw everything we could possibly have hoped for. We saw the emergence of, or the convergence of probability distributions toward a fixed form, which was not a Gaussian, so not trivial. We saw scaling behaviors, and this isn't the only one. For example, if you measure the correlations in time, which we didn't make any use of here, at larger k, so when you've coarse-grained more and more neurons together, the correlations of those coarse-grained variables slow down, but the form of the correlation function stays fixed, and the time scale grows as a power of k. It's not as clean as this, but it's very strong. Okay? So we see all of these things that are the phenomenological signatures of this theoretical apparatus. 1,500. So my view is okay, so it's also true that because we're seeing the convergence toward a non-Gaussian fixed point, if you really want to make the analogy to the physics problems, we're not here, we're not here, we're here, which is a very interesting place to be. And maybe that actually means something biologically, but we don't know how to do that yet. But what I think is really interesting is that when you go, we're actually now at the point where experimentalists can measure so many things at once that you can explicitly do the kind of coarse graining. You know, it's one thing to say, oh, things should simplify in the same way that molecular dynamics becomes fluid mechanics. Fluid mechanics is simpler than molecular dynamics. Something like that ought to work in biology. And everybody says, yeah, sure, right? But we've actually gotten to the point where there's enough data that you can actually try and go through that exercise, and you see all the ingredients that you were hoping to find. Now, what we don't have is a theory that puts all of this together. So let me stop there. Sorry, this went a little bit long, but we can come back and have questions after a break. Okay?
Okay. So, thank you. 10 minutes short break without coffee.
temperature, it's here, I don't know, right? So the coordinates here, if you measure them on the shortest distance scale, are about the properties of the real material. Then as you zoom out, what you find is that many of the parameters flow towards 0. So that already tells you that some features of the molecular behavior are going away. And in particular, if you tune the temperature and the pressure so that you hit this point, then what happens at this point isn't about where you started, right? It's only about what happens. It's like in dynamical systems. I have a fixed point, and there's behavior in the neighborhood of the fixed point. And so the thing I haven't told you is how do you connect the behavior of near this fixed point to something you can measure about the real material? Okay, that's a little bit more complicated. But for instance, if you have a liquid and you set the pressure right, then you know that, right, as you change the temperature, it becomes a gas. How do you tell the difference between a liquid and a gas? You measure the density difference between the liquid and the gas. At some particular temperature, that density difference actually goes to 0, and you can't tell the difference between the gas and the liquid anymore. So the way in which it goes to 0 follows one of these scaling behaviors. So the difference in density goes as the distance of the temperature from the critical temperature raised to some power. And that power is related to the flows in the neighborhood of this critical point. And it's a pure number. And it doesn't have anything to do with what the material is made out of. And so in that sense, it's universal because you've forgotten everything about the material. All that matters is that you arrived in the neighborhood of this point. So phenomenologically, universality is the statement that there are things I can measure about, let's say, the transition between gas and liquid. And if I use the right units, I can put all the different liquids and all the different materials on the same graph. Doesn't matter what they're made out of. Theoretically, it's the statement that those behaviors that are captured by that are determined by the mathematical structure in the neighborhood of this point and are thus independent of where you started. So there's this separation between where you start, which is the microscopic details, and what you see at the macroscopic scale, which is determined by the behavior in the neighborhood of the fixed point.
Hi, super interesting. I've got many questions, but I'll stick to 2, okay?
Okay.
So this supports the hypothesis that the brain is critical, that you have criticality in a healthy brain as a matter of good functionality of the brain, right? Could you take the brain out of criticality? So can you induce that in the rat, for instance, by sedating the rat or something like that, and see the route towards criticality and measure something like correlations that diverge or something like this?
Okay, so the question references a large literature. There's a long history. So if you look in the phase diagram of real materials, critical points are very interesting places. All sorts of interesting things happen there. Okay? Actually, the details are maybe not so crucial for most people in the audience. The idea that biological systems might be, in order to be functional, should be at some non-generic setting of their parameter values, that's a very old idea. And the idea that the nature of that setting, the special setting that makes everything work, is that it's somehow like being at a critical point in a physical system, or in a non-biological, in an equilibrium system. That identification is an old idea. And it's an idea that comes around in different forms, in different contexts. There are 2 questions. One is it true? That is to say, if you look at data, can you show me things that are the signatures of being at a critical point? And the other one is, why is this what the biology should do? So what is the principle that selects the parameters to have these values as opposed to any other values. So that's a question which is an important general question by itself, one that I've been very interested in, and the answer might or might not be that the correct, so I believe that it's a good way to approach these systems to think about what are the functional constraints that help to set the parameters of the systems that you see in nature, as opposed to all possible systems. It might be that those parameter settings correspond to being critical, or it might not. So you should kind of separate those questions in your mind. I think one of the difficulties of the literature is that these questions have been tangled up. So people write papers in which they say, it would be good for information processing in the brain if you were close to criticality. In truth, that argument isn't very tight or very strong. So what they mean by information processing and what they mean by critical and what they mean by close, all subject to argument. And then you see evidence of something that looks kind of like critical behavior in a real system, and it's also not very strong, but somehow together you feel better. So you have two weak arguments. So what we've tried to do is to stay away from this and say, look, I want to separate in my mind theoretical questions about what are the functional principles that select the parameter settings for the biological networks that you see in nature. Really interesting question, which you'll notice I haven't talked about at all. From the question of, when I look at large networks, do I see the emergence of something that looks like critical behavior? I would say that if you look at our modern understanding of critical phenomena, sorry, let me back up a moment. The things that we think of as critical phenomena are equilibrium phenomena. We can extend those notions to models of non-equilibrium systems, and in those models, I think I know what I mean. But then when I look at a real system, I'm not sure I know what signatures I have. I can't change the temperature and see whether something behaves the right way. Right. I don't know, if I have a magnet, what I do is I apply a magnetic field. What should I do to the brain that corresponds to applying a magnetic field to a magnet? I don't know, right? And so a lot of our tools for testing the notion of criticality are not available to us in these more complex systems. I would say that in our modern understanding of critical phenomena, the invariance of the distribution of coarse-grained variables is actually the most fundamental thing. It's not the scaling. It's the drive toward a non-Gaussian fixed point.
Right, so I guess
and so in that sense, I would agree with your first statement that this is pointing in that direction, but I think the connections to everything else, I think it stands on its own. Either you're convinced that this is evidence of criticality or not. It could be that tomorrow my colleagues come to me and they say, I can now record from 10,000 neurons, let's keep going, and that beautiful convergence toward a fixed distribution that we saw at the scale of 1,000 neurons wanders away when we get to 10,000 neurons. And after all, that's what you might expect from these trajectories. So we'll see.
You need some stationarity.
You always need some stationarity. So these experiments are of order an hour long. It's not so bad.
So, who had raised the hand on this?
Yes.
Yeah.
Thank you for the lecture. And my question, I actually had two.
That's okay, he did
Is
too. Go
the
ahead.
mouse's head open during the experiment?
Yeah, of course.
Yeah,
Yeah.
okay. And, and
It's right. It's actually a direct visualization, right? So you have to,
okay.
So with the electrodes, you can close things up. There are also strategies for making microscopes that have fiber optics coming out of them.
Yeah.
So you can attach them to the brain and close everything back up. So there's different strategies. They have pluses and minuses.
Okay. And about that final distribution you talked about, in terms of neurons, what does it represent?
So literally in this case, if you think that what the fluorescence signal is measuring is a proxy for activity, then the variable on the x-axis, which interestingly is called x, is in fact just the summed activity of k neurons, of a cluster of k neurons. and leaving out the parts where that cluster is silent. So you're asking, when I group K neurons, when I group 32 neurons together, and they are 32 neurons from a neighborhood in the sense that they were all strongly correlated with each other, what's the distribution of the summed activity? And the answer is that when I go from 16 to 32 to 64, the distribution hardly changes at all. And that's not because it's Gaussian. It has some other form. And so that must be because when I average these 16 with these 16 to get to 32, each of them look approximately close to exponential, and they're correlated with each other in just the right way that when I put them back together, I get an exponential again. And amazingly, that keeps reproducing itself at every stage. So phenomenologically, that's what it means. What it means more deeply, we don't know. So yeah, probably that's what you wanted to know, so sorry.
Okay, so the way you coarse grain your neurons by adding the two most correlated together and then going to the next two, it's very similar to building a phylogenetic tree, right? You have species, you look for the two most similar. So can you build a dendrogram out of that?
Well,
and look at it?
So
do you see clusters
in this case, the way we did it, so if I may, if I go back to here, right? The fact that I took groups of 3 and did majority rule, I could have picked something else. I could have picked groups of 5. Instead of doing majority rule, I could have just averaged things together. I could, there's details of the coarse graining that are arbitrary.
Yeah.
So we picked something, and as I said in answer to Stefano's question earlier, in fact, we picked 2 things. We had one which was in this sort of group things together, and the other which was to go in using principal components analysis. The way we did this, the tree is trivial, right? It's always pairing.
Really, but I mean, for instance, suppose you take neuron 1 and 2 and put them together.
Yes, we then,
at the next step.
but now okay, so what we could have done was to ask, what's the next most correlated? Instead, what we did was, we asked, what are the next 2 most correlated neurons? So we wanted to do the analog of what you're doing here, where you group things together.
Okay.
Somebody was worried about overlap,
yeah,
so we do it without overlap.
Oh, without overlap, okay.
Okay.
All right, okay.
So if you keep going with these ideas, would you expect a kind of new universality class in which most of biological systems maybe fit in? Or
what you're asking for is the structure of the theory which is at the end of this coarse graining process. So what is the theory of that fixed point? So first of all, the idea that the way you should think about these big complicated networks is by coarse graining them and making a theory of the fixed point instead of a theory of the microscopic network. So that's an interesting idea. And I think what we've done is to provide evidence that that theory will be simpler, because there is a fixed point that isn't, you know, just something, or it isn't complicated, right? There's something simple at the end of that. And so we'd like to find that theory. What you're asking then is, when I find that theory, am I going to look at it and say, oh, right, I know this one. It's something that I can find in the statistical mechanics literature. Of course, the hope is, no, it will be something different, because that would be the most interesting possibility. But you know, if it turns out to be, so, I mean, it's not obviously any of the ones we know about. I think we would have figured that out, but we could be missing something. So there's a chance that it is indeed something different. But since we don't have our hands on it.
Okay, one last question. Yep.
So I also have 30 seconds at the end. So.
So is there, suppose we want to find this theory that lies at the fixed point, what are the approaches for sort of this inverse problem, right? It's not, it doesn't seem trivial to me to find that.
If I had a really good answer, I'd be some part of the way to the answer to the harder question, right? I don't know. I mean, I don't think this is a somewhat different situation than we usually find ourselves in physics, and so I don't quite know how to do it. So, let me say one thing at the end, though. Since this is a school, I think this is important. So, this project is the PhD thesis of one student, Lenoy Meshulam, who's now a postdoc at MIT. And when she came to Princeton to begin her PhD, she talked to me about doing something theoretical. She talked to David Tank, in whose lab these experiments were done, about the kinds of things that were going on in his lab, and she wasn't sure whether she wanted to do theory or experiment. And she also talked to Carlos Brody, another colleague who, in particular, was pushing not the technology for recording from the neurons, but the technology for getting the animals to do more interesting behaviors, which, as it turns out, wasn't so crucial for this project, but okay. And after we have in the PhD program in neuroscience, unlike in physics, we have a rotation system where students spend a few months with each of several advisors, possible advisors. And at the end of spending 3 months with me, 3 months with David, and 3 months with Carlos, she said, okay, this is really interesting. I think I should work with all three of you, and this is what I want to do. And so this came at the end, so there were many steps in between. But it is interesting. David Tank and I have known each other for 25 years. And although both of us had done many things in neuroscience, we had never done something together in neuroscience. So this is one of those examples where adding one student who has interests that connect the work of different faculty members really makes a difference to the trajectory of the science. And I think that's an important thing to keep in mind as you all try to find your way, right? It's not always finding one advisor who does one particular thing and you want to work on the next step in their particular research program. If you're lucky, you can find situations in which your combination of interests can perturb the trajectories of several faculty members. It doesn't always work, okay? Also, having 3 advisors can, I understand, be somewhat problematic, especially if they're all very insistent, to put it politely. So, so there are challenges, but it is also, of course, incredible fun for those of us on the other end of it if it works out this way. So anyhow, thank you.
So, thank you again. And you want to say something?
Yes, so